about this material before, and I will start with some algorithm and some definition of the data, and after that go to the main material, that is RX algorithm in the kernel space. Okay. First we assume input vector that is xn, it's equal to this is the vector for each entry of the data. It has the j value for each entry, and all of the data that we will use x sub b, that is the matrix of all of the data, x1, it's the whole data. It's a matrix by j n, and the j is the number of the entries of each data, and the n is number of all of the data that we have. And there is two hypotheses. Hypothesis 0, that it's in hypothesis 0, they assume that we don't have any signal. It's all of the data are noise, and in the hypothesis 1 we have signal plus noise, and the algorithm wants to detect the signal in the input data. The RX algorithm, the conventional version of the first version of RX algorithm is use this equation, r minus for detection of the signal in the all data in 1990, I think Reed and as a student work on this algorithm and find the value of this equation can shows the, for example, signal in the set of the data. And here R is the
I hate to interrupt, especially in front of the camera, but you have to explain what this algorithm is for. Like,
okay. The algorithm it's for anomaly detection. For example, you have a signal and you want to detect some part of the signal that is not similar, or it's the difference in the, for example, if you have the original one of this algorithm for the hyperspectral data, and in the hyperspectral data we have spectrum of the, for example, ground, and based on that we wanna, for example, detect some small things in the ground that's, for example, it's something that's it's the human made things and it's used for the military. By this algorithm, using the mu is the estimated mean of data. If we wanna, for example, decide about one special point in the, for example, an image, we must find the estimated mean and estimated covariance of the neighborhood of that point, and based on these these two metrics, we can find a value by this equation that shows this point can be, for example, ordinary point in an image, or it's, for example, anomaly. If
What is X? The first equation.
this one,
Yeah.
this is the input data. For example, you have n-dimensional data, and here is the j-dimensional data. For example, you have, for example, for first observation, it's the, for example, j coefficient that shows the first observation.
You mean the hyperspectral image?
Yeah, in
G
hyperspectral
is for different spectrum,
spectrum, yeah.
and N is for the dimension of the image.
N is all of the data that you have. You can reorder the data in the one vector, that it's the total number of data.
So, for example, your image size is maybe 3 by 3.
Yeah.
Then N equal to 9, right?
Yes, and if your, for example, you have a hyperspectral image 3 by 3 and the spectrum is 10, the xn is, for example, xn1 to x10 n, and the size of the xb is 10 multiple 9, because it's 3 by 3.
So the N is
N is the, for example, this one. N is N is between, for example, here between 1 to 9. It's 1 point. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9.
why is the notation is set up in this way? Is it coherent?
Yeah, you reorder the data to two-dimensional matrix. Maybe you have more than 2, but you reorder all of that to the two-dimensional matrix and do all of the, for example, calculation of that.
So N is not equal to 9, it's between 9 and 9.
Yeah, because it's, for example, it's I,
Oh,
and
oh yeah.
this one is I. It's 1 point in the.
So
Can you repeat again what's the objective of your algorithm?
For example, if we have a signal like this, we want to find some part of the signal that is not similar to the all of the part. For example, if we have signal
Do
something
you
like,
remember the keyword?
yeah, anomaly detection. Yeah, for
Can you
anomaly.
write it down?
Yeah.
Rx, the parameter R is a point?
Yeah, it's a point that we want to decide about that point. For example, classify this point as a signal or as a noise.
This equation is more like confidence region.
Like
Confidence region, because you have the quadratic form. This is
What do you say? Like what?
it's like
Confidence
confidence region, like confidence interval.
Oh,
Confidence region.
confidence.
Yeah.
I mean, the whole thing is so simple. I don't know why it makes it so complicated. when you
yes,
say
because
it. I mean, we just try to do anomaly detection. So because anomaly doesn't appear very often, right? So you can just use all the rest of data to estimate the covariance and mean, and then you just see like how far from that covariance and mean is far away. Then assume it's anomaly. And I mean, I hate to say that, but don't call the equation an algorithm. It doesn't make sense.
okay. And if we have enough data, we can simplify the RX algorithm to, for example, this version. For example, if we have enough data and goes to infinity, we can rewrite. Yes, and in the this equation, it's more common and it was used in the papers and different application for anomaly detection.
So R it should be a vector.
Yeah.
This vector is from which part of image is the R?
For example, in hyperspectral image, you have for each pixel, you have a spectral pixel. It means, for example, if this location is, for example, x, y, the, for example, data of this point, if I use R, x, y, it's it has more than one number. It has J number, for example.
Okay, it's a hyperspectral, it's all spectrum.
Yeah.
Okay. And the mean mu b is the mean of that
Mean of the
spectrum.
all estimated mean of the data.
It's a mean of all data.
Estimated mean. Yeah, because we don't have all of the data. We have some captured data, and based on that, we estimate the mean.
That should be estimate the mean for that particular point. We want to see how much the point deviates from the expected mean.
Yes.
Okay.
But when you wanna find the mean, you don't have all of possible data. You have some portion of data, and based on that, you decide about, for example, the mean and covariance.
So mu b, you should, how do you get mu b?
For example, you have the data, xb, it's a matrix, j row and m column, and you can, for example, do the summation on that. It's the signal, for example, I equal to
Okay, so you go through all the points and take mean of the
yes.
all spectrum.
Yeah. And variance can be, for example. Yeah, let me write it down as this way, for
What's the
example.
M here? The capital M?
M is all of inputs. M.
Is all the pixels?
Yeah, all the pixels.
3 by 3 by.
Yeah, for example, here is 9.
It's 9.
Yeah. Okay, and
In this case, mu B is the average of given spectrum.
yeah, I have, for example, if we assume, for example, xb is equal to, for example, 1, 2, 2, 3, 1, 3, 4 minus 2, and 2, 2. Okay. The mu b is equal to 2 and 1.6. Summation on all of this row, these two rows, and divide by the number of it.
So each row is an image in a given spectrum.
No.
Right?
In this one is, for example, in a spectrum of with 1 point. We have, for example, 5 pixel in our image, and each pixel has 2 numbers. It's a fake example, and CV is equal to 26, it's equal to, for example,
Should be xi and xj.
yes. Uh,
It should be dimensional, not dimensional.
yeah. For this data, it must be I'm not sure about. in all of the when we work with the different set of the data, it's not easy, for example, to classify all of the data with this algorithm. In some cases, we need to move to the data to a higher dimension space, and it's give more freedom to classify data. And
map one point see x and y. The spectrum, for example, Reynolds J, you map to higher dimension.
I didn't map anything. It's ordinary case in the original space. But it's possible to move the, for example, map the data from the, for example, input space to second space with the higher dimension or different dimension space.
So by the original data, you mean the each input pixel.
Yeah. For example, each input pixel, for example, if
J dimensional.
yeah, if we have R as input, it goes to the, for example, phi R in the second space.
So map from J dimensional space.
Yeah,
to
from, for example, to J dimensional space to, I don't know, to P dimensional space.
Okay.
Okay. And there is a trick. Its name is Kernel trick. That it's for example, it's if we need to, for example, have a dot product in the second space. In ordinary case, we must, for example, if we have, for example, x and y as two inputs, and we want, for example, the dot product of, for example, phi x, phi y. We need, for example, map x to the second space and y to second space, and after that doing dot product. But it can be equal to using a kernel function between x and y.
Phi transpose x. Oh, you mean dot product?
Yeah, dot product. And this kernel function can be, for example, a simple norm function. Or any kernel function that only use the differences between data in the ordinary space and do a mapping in the and it's not necessary to doing map all of the data from the first space to second space. There is some example for that. For example, or some function like this, it can reduce the complexity of the algorithm in the second space, because mapping this data in the second space and after that doing all of the algorithm, it's not easy. Now, I will explain the kernel version of this equation in the, for example, any kernel, with using any type of the kernel. If we kernel, any kernel like phi, which can change the, for example, hypothesis of, for example, of problem to the this hypothesis, it means, for example, we want to detect anomaly in the another space with more freedom. It gives us the ability to have separated data in the second space, and this equation will change to, for example, phi r minus mu b phi hat and cd in the here the mu and mu and covariance matrix.
This is minus mu or mu phi, because you have a phi outside.
There.
Because this is original space, you need to minus mu from Anomaly. That's it.
And the set of input data for the make a short form of the equation. After that, use phi sub c xi instead of this term. Okay, it means it's the biased version of the data. For example, we calculate the mean, and after that subtract the mean from the original data and make a unbiased data. And for example, this equation is 1 over m y c xi. SCA to find the we can find the eigenvalue and eigenvector of the covariance matrix in the kernel space. We use that, we define V phi and omega, big omega B and B phi, and this is the eigenvector. This matrix is diagonal matrix that all of the elements are eigenvalues.
This is SVD. You are trying to
SVD,
write
yeah. But in SVD we I think in SVD the dimension of this matrix is not a square matrix.
So this is eigen decomposition.
Yeah, it's decomposition. Yeah.
Is there a transpose in the B?
Yeah, the second order transpose. It's fine. And V phi here are V phi 1 to V phi n. Each n is the maximum number of the data. That's it's possible to we have some zero eigen values, and if you have some zero eigenvalues, it's not necessary to add that columns to this matrix. And because in the here we need the inverse of the covariance matrix, the inverse of covariance matrix can be we do the reverse matrix on this diagonal matrix. Now we want to change the format of this equation. It's kernel tree format that we can calculate the value for each point in the each point of the data without the transforming the original data to the kernel space. These eigen values are, for example, a linear combination of the data in the second space. For example, I can write it down as the summation of beta ij. Let me write it down for only one of them. For example, if I want, for example, v phi rj, it's equal to beta ji, and it's the summation of the data in the second space. It can make one column of eigen vectors. And if I want to, for example, write it down for v because of this, for each column of the eigen vectors, we have vector of the betas that is equal to beta 1 to beta m of the same column, and the v5 for all of the data is can be there, for example, xb5 multiple the matrix of b1 to beta n. Okay, and for DC, the equation we use this B as this matrix. And if we replace this equation into this, it's equal to, for example, xp5.
What is XP5?
xp5 is, yeah, let me write it down. xp5 is phi c of x1 to phi c of xm.
It's a real vector.
Yeah, because the eigenvector are the combination of the original data, and because of this we can, for example, find the betas as numbers that make a big matrix, that if we calculate this matrix to the original data, we can find the eigenvectors of the data. And I can replace it here with
X or
okay. Okay, this one is the c minus 1, and in the kernel, and if we replace it with this equation, it will be equal to r.
This is the B capital B is that beta.
The capital B is this matrix. It's n by n, n by j matrix.
That one.
No, this one. This one is big.
Oh,
Each one of
Each
this
of them.
column or this.
okay.
And I want to replace this one here, and it will be keep the summation here. We have a CB5 minus 1 as XB5 beta the omega minus 1 B beta transpose XB5 transpose. Big D is beta 1 to beta n, and beta I is equal to beta 1 beta I1 beta J I. Beta N. Now I'm gonna multiply these two and these two together, and it's 5R multiple XB5.
So the transpose.
This was transpose. Yes. Yes. Okay. This one and for what? This is this one is all of the input data. It's 5x1 to 5xn, and this one has this one it has a for example phi c x is phi x minus mu hats d phi. Okay. And because of this there's another term minus 1 over n. This one is the estimated mu, and it's 1 to n of phi xi. It means all of the columns must be unbiased. And now I can do the kernel trick and use it instead of the inner product, because there is the inner product of phi r to x1, and I can replace it in this one with the k r and x1. K, R, and X, N. minus this term must be multiplied with this one, and this is 1 minus n, the k of r xi. Okay. We consider data it's from x1 to xn. If we find the kernel function with all of the possible data, it makes a matrix. For example, kx1 1 to k x1 n xn k x n x1 k xn d all of finding the inner product or kernel value between all two possible value in the in data. You can see here, this one is if we have R is 1 point in this data, this value, this vector, it's one column or one row of this matrix. Because of this, it's not necessary to calculate this value every time. If you calculate all of this, you can select one column on one row of this as this value, and if you have this one, you can find the mean value of each column or each row. And we use KTR for all of this value in some papers. This term referred as KXBR transpose. For 1 point, all of the data kernel value of all sent unbiased data and the points that we want to find the value. And this one is the minimum, it's the mean value of this vector. Okay, and here for the second one, it's mu b5 is b5 this mu is 1 over n 1 to n 5 x5, and for this one it's all possible data, it's x1 to xn. Oh. It's x1 to n, and and this one is not centered and it must be minus
Is there still transpose there? The mean.
this original data unbiased. Okay, that's it. And again, we have the multiplication of dot product of two inputs, and we can rewrite it as 1/n. Sigma 1 to n, and here the vector of k x I x1 to k x I xn minus 1/n. Here we have 1/n, and it's 1/n square, and I equal to 1 to n, and j equal to 1 to n, k xi xj. Okay. Again, this step is one data, and it's one row, one column of this, and this one is the mean of all of it. For example, you add all of the integers of this matrix, and you can find that point, and it's k t here we can, for example, same as this 1 and 2, we can use, for example, kernel function for the dot product between this data to this term, and it will be changed to
First term is multiplied. You have to multiply related analysis. So the first
here,
below first term there.
this one,
Down
this,
here.
yes, xp. xp here must be centered and unbiased, and we subtract the mean of all of the data.
How come you should have a scalar, right?
Yeah, it's for example, for each
Yeah, you have a
column.
scalar, then what was the first term in the summation there? Like what is kxi xi? Isn't that you're writing down vector here?
This one,
Yeah.
yeah, these two are vector.
Then you got matrix here.
The output of the k, it's a number, and it's the vector. For example, 1 to m, and each entry in this matrix must be subtracted from this value. This is only one value.
I mean the final term is a scalar or vector.
The final value is a vector.
It's a
It's
vector.
the same size with this one, because we need to subtract these two, and it makes
No, it's okay. It's okay.
yeah. And if I replace that value, it's became KRT minus K mu B T. Okay, for these two, and we have a decay that I will explain it. -1b and kr t minus k will be t. And here we need to find the covariance matrix in the second space. We call this value as dk. It's contain all of the kernel kernel function value between the input data, and if we want to find this value, because here we didn't subtract the mean value, and here we need to have unbiased data, and because of this there is there's an equation that we can, for example, find the k value, the unbiased value, which is kb minus, let me write it down as this way, bonds n over n multiple kb minus kb multiple bonds n over n plus bonds n over n kb bonds n over n.
What's KB half? What's it?
kb is this one.
So the KB half is
kb hat is the matrix that is biased. For example, we used here the unbiased. Here we subtract the mean value of each point, but in this matrix we need to, for example, find the value each point and the minimum and subtract it, but we can estimate it with this equation. If you multiply n by n matrix of 1 over n, it means you get mean value of each row. In this one, it means you get mean value of each column, and this term is the mean value of all of the entries. And if you do something like this, you will subtract the mean of each row, each column, and because you do something 2 times, add one of them. For make the KB unbiased.
matrix or?
No, it's a square matrix. All of the entries are 1. It's m by m that all of the entries are 1 over m.
It's the average of each column.
Here is average. It's it's average of column of, but it's a matrix. It's not a number. Okay. Did I have time? Yes.
How far?
I think it's half an hour at least. I need half an hour. It's 3:40 till 3:35, and I think it's take for example 1 hour, half an hour. Continue or
Yeah,